Welcome to week 4. This week we are talking about wildlife populations and assessing the abundance and density of those populations. And here are some different techniques that are used for you to look at. If you want to study this, you can go to the actual PowerPoint that's in the classroom. So we're going to have an overview first of wildlife population sampling, the estimating abundance and density, methods for marking wildlife species, looking at bias and precision of the estimators, closed population models, which are Lincoln, Peterson, Schnabel, and models M sub-tac 0, T, B, and H, and open population models such as the Jolly-Sieber model and the CJS model. An index is a count of animals or their sign that hopefully contains information about relative number or density, but it is not an estimate of these measures. Examples of an indices or an index is the number of animals seen while walking a transect or sitting at a point, number of frog calls heard per minute, number of rodent burrows per hectare, or number of deer shot or muskrat harvested per season. Ideally, a relationship between the index and the population's size, n, is linear and constant. Often the relationship varies in space and time, which can make it difficult to use the index to monitor population change or to assess management treatments. So the estimate of abundance, or n, is the count of animals divided by the estimated probability of detection. And then it shows you count over P. Census is a rare situation in wildlife studies in which detection probability equals 1.0 and all animals are counted. Animals can move, so one cannot conduct a census that captures every animal in a given area. For example, the U.S. Census is not really a census for the same reason. It is an index. Other methods of estimating abundance, such as mark recapture and distance sampling, allow for detection probabilities that are less than 1.0. Mark recapture analysis has been applied to numerous issues in population ecology and conservation. Estimation of population size and finite rate of increase for monitoring studies, impact assessments, and harvest models. Estimation of survival parameters as part of a population viability analysis for threatened and endangered wildlife species. An estimation of survival, emigration, and immigration to test hypotheses about population regulation, source sink dynamics, and life history trade-offs. It's used quite commonly. An active area of research for biostatisticians, and it has become very sophisticated. In other words, hard to understand for us mere mortals. Most methods rely on uniquely marked individuals. Common approaches are ear tags for mammals, leg bands for birds. That's some that many are aware of. Another method that's been used is a pit tag, a passive integrated transponder, and they're used mammals, fish, and herps. A pit tag is typically inserted under the skin of an animal, similar to how we now use tags, electronic tags, to identify our pets. Another method is the visible implant elastomer used in amphibian studies, and I have seen this done injecting a tiny amount of paint in a variety of pattern and colors just under the skin so that the animal is recaptured and you can tell it's an individual using ultraviolet light. Radio telemetry can also be used to estimate survival rates, and most of us have seen animals with radio telemetry collars on them on, for example, like the Discovery Channel or someplace like that. Investigators have developed other ways to mark and recapture individuals. I know in the past we used to clip salamander toes and use a set pattern so that when we recapture them, within a several month period, you'd be able to tell you had the same individual, but they do grow the toes back over time. They most likely don't do that anymore. Rarely would you see that because of the concerns of animal cruelty. But there are quite a few unique ways to mark and recapture. Sometimes it's spray paint on a squirrel. It can be a lot of different things. For example, you photo identify whales based on pictures of their tails. They can tell that from the different patterns when they have the same individual. Fin whales are similar. You can use photos of fins and use them as unique identifiers for those species with fins. Brown and black bears are monitored or populations tracked using DNA. Bears are known to rub up against tree bark, and so hairs are left there in the tree bark and they collect them. Wildlife biologists go out and collect the hair that's caught in the tree bark and then go through DNA analysis to identify individuals. The estimators, a parameter is the true population value of interest, such as population size or annual survival rate. The estimator is a mathematical expression that indicates how to calculate an estimate of a parameter from sample data. The main approach used in statistical estimation is the method of maximum likelihood. The two criteria to judge are bias. If we repeated sampling under the same conditions a large number of times, and each time computed an estimate, the average of the estimates should equal the parameter of interest. And precision relates to the repeatability of a result and is measured by sampling variance or its square root to find the standard error. So here's an example of targets and patterns and how precise a parameter estimation can be. So the first is unbiased and precise, very close together. B is unbiased but not precise, so you can see kind of a scatter. C is biased but precise, so that's off to one side, but it's very tightly patterned. And then D is biased and not precise, so you can see it's scattered and not close to the actual population. And this basically shows you the same thing about where the mean is and how it's falls under each of these different